So here's a question. What is the joint density function for the order statistics? In fact, so see, if I knew the joint density function for the order statistics, then maybe I could even use that then to get the marginals, know the behavior of the first one, and know the behavior of the second, the behavior of, say, the second finishing time, and the behavior of the kth finishing time, all right, so I don't know. I really don't know, but let's consider a similar problem. Let's just go back to the random variables x1 through xn, and remember those guys are independent, right? So I'm going to draw this little picture here. X1 is there, and right here I'm going to have x1 plus dx1. Okay. So that this amount is dx1, right? And then maybe I'll put x2 here. And right here I'll put x2 plus dx2. And over here I'll put, maybe put a resistor between these two. No, just kidding. This is the symbol for yada yada yada, bunch of stuff in here, and then finally we come over here and we have xn. Okay, so maybe we have a whole bunch of other x's in there. Okay, xn, and then this is little xn plus dxn. Okay, so that these are all little differential lengths, tiny little amounts of time, say, maybe, or space, or whatever. Okay, so let's keep this picture in mind. What is the probability that x1 falls into the interval between x1 and x1 plus dx1, and x2 falls in the interval little x2 to little x2 plus dx2, and ... xn falls in the interval xn, comma, xn plus dxn. Okay? Well, these are all independent. These x's are independent, right? So I'm sort of asking, what's the chance though that the first one, or not the first one in time, but the one labeled number 1, that the number 1 x falls in this little interval, and the number 2 x just happens to fall in this interval in the next one, right? And that they sort of go in order like that. By independence, and remember, these x's are independent. The order statistics are not. But by independence, this is just the same as the product, right? The probability that xk falls inside that little interval from little xk up to little xk plus dxk. Okay? Okay. Oh, k goes from 1 to n. Now, this is what is this? This is basically, I mean, that's sort of the meaning of our density function, right? K dxk, right? So see, that's really like, the probability density function evaluated at x1 times dx1 times f of x2 dx2 ... times f of xn dxn, right? Or it's, you could rearrange that to write it like this. Whoops. Okay. F of xn, and then dx1, dx2, dx3, etc. to dxn. Okay, so how is this related to the joint density function for the order statistics? Well, I'm glad you asked. So take a look at this picture here. What we've just come up with is actually, if you take a look at this, this is the joint density function for x1, x2, etc., xn, evaluated at x1, x2, etc., little xn, right? That's what this joint density function is, and I know that it partitions that way as the product of those marginals because they're independent, right? All right, so let's take a look at this picture now. So I've got I'm basically describing the chance that x1, and I'm thinking of 1 in this case, is not a time index, but as a label. Okay, maybe we have runners with tags on their shirts, and we've got x1. 1 in this case means the runner labeled number 1, and then runner labeled number 2, runner labeled number n. Okay, we've basically come up with a density function expression for that describes the chance that runner number 1 falls in here, and runner number 2 happens to be second, and runner number n happens to be last. It falls right in there. Okay, so what I really want to be able to do, though, is write down an expression for the density function for these order statistics. All right, joint density function for the order statistics. So I'm going to start by thinking like this. I'm going to multiply by all these little differentials. So this is the probability that x1, the minimum of those, actually does fall in that little interval from x1 to x1 plus dx1, comma, and go up to the maximum there. This guy falls in xn to xn plus dxn. So here's what I'm going to observe, and I hope you will too, and that is that this should be very related to this. Okay, this describes the chance that runner labeled number 1 falls in here, runner labeled number 2 falls in there, etc. Now, I don't really care which actual runner falls in there when I'm talking about this kind of thing. Okay? I just want any one of them to fall in there, and then a different one of them to fall in there. So, this probability is really, it should be, in fact, this probability, but then you've got to multiply by all the number of ways to arrange the runners in those intervals, right? I could put the first one here, second one there, and then the nth one there. Or I could put the second one there and the first one there and the nth one there. Or I could put the nth one here and the second one there and the first one there, etc. How many different ways can you arrange the runners in these tiny little slots? N factorial ways. That's the answer. Yes. So in fact, it should just be n factorial times this answer up here, right? And it is f sub x1, f sub of x2. I said sub, it's not sub, it's just of. Okay? And so, in fact, this gives us the joint density function. This is the joint density function for the order statistics. This and this are the same. Okay.